Okay, welcome everybody. I already wrote what will be the topic of our next lecture, of our current lecture. So now we are getting into the main event. That is the okay. So previously we criticized the standard formulation of quantum mechanics, attacking it from the angle of the measurement problem. We discussed why it is a problem, not a measurement solution, well, I argued that the measurement problem cannot be solved within the standard formulation because of how it's structured. So that would be our critique and motivation why we would maybe try to reformulate quantum mechanics in maybe some better way, or at least a way that won't have the same problems as a standard formulation. So we are aiming for something that will be similar to Hamilton reformulation. We are not trying to invent new theory or something like that. We just want to see if we can do something about the standard formalism. Maybe you can improve it. And the battle plan is that we will, instead of trying to guess, what kind of improvements are needed there, as it's historically, this is how usually people approach this issue, by trying to guess or postulate what has to be done, what has to be changed or improved. Instead, we want to do it, like go back to basics. We want to role play as someone who doesn't know what quantum mechanics is. We just pretend we never heard of anything about quantum mechanics, and we want to try to deduce what is the shape of the theory, what is the formalism from phenomenological observations only, without bringing in any assumptions about the structure of the theory, right? So we are trying to emulate what people did 100 years ago when they invented quantum mechanics, right? However, we have 100 years of development of science overall, right? So while the pioneers, they focused most likely, and this is my reading of the history, that they focused on the case of experiments that ended at the first instance of measurement, right? So it's a single measurement experiments essentially. And when you focus on that, let's say, and you are very smart, you can deduce the formalism of a new quantum theory, and this formalism will probably look like the standard formalism. That's my assumption, right? So what can we do to not just repeat their steps? So my proposition was that, okay, so they were focusing on single measurement context only, and the description, how to describe a sequential measurements, okay, when the experiment doesn't end at the first deployment of the measuring device, that was like an afterthought 100 years ago, because it was, the very fanciful idea that you could actually do experiments like that on quantum systems. So nobody thought about them too deeply. So there was a post hoc solution invented for, how to essentially jury rig the single measurement approach to multiple measurements, and this is where collapse rule comes in. So my proposition is to let's try to do this deduction from phenomenology, but use sequential measurements as our basic input, basic phenomenological input, and hopefully, when we start from sequential measurement, this will be our basic setup. We won't be funneled into the same path as people were 100 years ago, and perhaps we will be able to find out something different than the standard thing. Okay. So, in other words, so in this first part, okay, so now this is like a motivation what we'll do. So our so we'll split this whole discussion into two parts, right? The first part will be as it's written on the screen. The first part will be description. We'll collect the experiments. Okay, we'll collect the phenomenology. We'll discuss on the way. We'll discuss, some maybe make some comments about what we are seeing, but we will try to just describe what we are seeing. Okay. And then we will, when we finish with that, we have our collection of inputs. We will go to the second part where we will just use those inputs to do the actual deduction, right? To conclude from that what is the shape of the formalism we are trying to find. Okay, so first we will focus on experiments, and those experiments, right, will be there will be. I will cherry pick what kind of experiments we will consider here. Okay, those experiments will be described in terms of like multi-time probability distributions, which is like the most let's say agnostic way to describe what you observe, and I lost my train of thought. Sorry. Okay. All right. I lost my train of thought. I had some good something to say, but I forgot what it was where I started saying. All right. So okay. So in other words, before we start talking about experiments themselves, right? First, I think we have to like review how we will describe those experiments, and like I mentioned, it would be a probabilistic description. So, let's spin the story. So imagine that we have our experimenter. We grab some student, lock them in the basement or something, right? The poor student has access to some collection of measuring devices, and they can then deploy those devices, right? They have their experimental setup. They can deploy those devices at some certain point in time, and then this device, when it's deployed, it does something, and it displays for the experimenter some result. Okay, so we'll have a collection of devices that, let's label them, that they are measuring some observables. So we have, for example, observable F. Observable. And this observable is measured by certain device. We'll call it F device. Okay, so F device measures some observable F, whatever that observable is. Okay, and when this F device is deployed at certain point in time by the experimenter, right, and it will display for them one of the possible results. Okay, when the device is deployed, at certain point in time, t, it displays one of one of the possible results. Results f, small f, okay, which is an element of some, the set of possible results of this device, okay? And we will assume here that we are only considering a finite sets of results, okay? So there is some, some number of possible things the device can display for us, okay? Yes?
It's a device. Can you tell here that, okay, I just have some, this is a digital display, for example, and it can show you the several numbers, or is it so that they appear as a quantization?
It has the display, and the display can, it can only show you a finite number of results. Saying that it's a, we assume quantization.
But it's a quantization of the physical, but just.
This is how the devices work, okay? And basically, about those devices, what are they? I think we don't have to specify too much about how they work, what they do. The only real assumption we are making here is that they do their thing, whatever that thing is. It's localized. Whatever they do is localized in time. Okay, so when we deploy the device at some time, it does something. Okay, and what it does can be considered as essentially instantaneous. That it's, we will this assumption I will mention when it will come up. Okay, there will be a point where we can look at some experiments and consider, okay, could this experiment be done with a device that takes its time and measuring stuff? Okay, but this is essentially the only assumption we're making at this point, that it's the device, whatever it does, it's localized in time. Okay, and that whatever it does, whatever it measures, the results it can display is one of the results from the finite state omega f. Okay. All right. So this is what the experimenter can do now. Like now, let's consider that they are locked in the basement, right? This is the only thing they do. They do the measurements, and now they take those devices and start deploying them, right, in sequences. Okay, so now the experimenter, they have their devices and they start deploying them in a sequence, chronological sequence, right? And they experimenter deploys.
So you assume that it is possible.
Yes.
Because it was not possible for many years, and it's so that it's something having some dinosaurs
Ichthyosaur very specifically.
This is a very strong assumption. You assume that you don't destroy the system.
I mean, look, if I said this about, we are pretending we don't know anything about.
The mechanism was not designed in this way. Because in the experiment, such repetition was not possible.
Yeah, exactly. That's what. So
nobody cared about.
Yes. So that's we discussed that on the previous lecture, right? So this was a like obvious limitation. That's why people focus on that. But we assume we are advanced enough, we can do it. And this is kind of, we can, we don't know that there is quantum world. I mean, pretending we are pretending we don't remember there is a quantum world underneath. So this is a this could be a description of a classical experiment as well, right? Your devices could be, cameras or something like that. You take pictures of billiard ball rolling around, right? It's the same setup, right? And you can say that you are doing sequential measurements. And here, if your collection of your devices and the system you are working on, it's, I mean, if your devices are not sufficiently fancy, right? Even if you are measuring electrons or something like that, electron gas, you won't see any, an indication that this is a, quantum system. If your devices are, not sensitive enough, or maybe they are just lying to you or something like that, you will see something mundane, right? But we will labor under assumption that we can find such devices that when we will deploy them, we will see something interesting. Okay. In general, this is not always the case, but we want to find some experiments where something weird is going, right? And we will. This is what we will be talking about, right? Because if we cannot detect that something is, we are dealing with non-classical theory, we wouldn't know that there is something going on. So the assumption that this can be done is of course necessary here, right? But the setup is agnostic of the fact that there is some quantum world underneath or something like that. Okay, so experiment deploys their devices and they get some kind of deploys devices in a chronological order. So let's say they start with F1 device at time t1, okay? Then F2 device. They have whole collection of devices, okay? Could be different, could be the same. They have whole collection of devices, okay? And they are labeled with, okay, this device I believe measures observable F3 or something like that, or whatever. I call it spin, let's say. This device, we have some collection of devices. We don't know quantum mechanics yet, right? So it's just a bunch of machines that we can turn on, and they do ping, and we can note the ping on the piece of paper. This is what we are doing, right? And hopefully we can find the collection of devices that will reveal something weird about our experiment. So in most general approach, each device in sequence will be something different, but those devices could be the same devices as well. But we won't constrain ourselves at this point yet. So then you have F2 at time t2, blah, 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 continue on, and then terminating experiment with some Fn device at time tn. So the results that our experimenter now records, we can arrange them in a sequence. So we will use the following notation. So we will have a Fn with an arrow, so vector-like notation, and this will be. So this is the result read from the last Fn device, Fn minus 1.
And at each device, each measurement is only one result.
Yes. Yes. So device displays something. It always displays something when it is displayed. Well, you can repeat it by doing if you choose the same device, or same kind of device in your sequence, and you repeat it.
But she's thinking about repeating,
Collection of
starting with the same initial state and repeating.
Ah,
Okay?
of course. I mean,
That's what she is thinking about.
yeah. I mean, you to collect your data. I mean, first let's describe one.
That is fair.
This is the first one. Okay. Of course, there will be repetition because we are collecting data.
It's a sequence.
Yeah. So this is one shot. Okay, and the data can be represented as this kind of vector, or formally n tuple. So this is.
Shouldn't you add argument t to this? Because
There will be about it. So n tuple is a sequence, okay? And the name comes from, because we have quintuple, sextuple, septuple, when you have like, the collection of 5, 6, 7 elements and so on. So mathematicians use this name, not only programmers also. If you use Python, you probably use tuples all the time, right? Cool. I don't know. I have no idea. So this is, Hubert might be right. In Polish, tuple is probably krotka.
and krotność is correct.
Because n-krotność. Yes. Yes, okay. So,
To make it short, it's
Yeah.
krotka to have different krotność.
so this is tuple because the order matters, okay? Because this result is one of the guys that sit in the possible results of device F1, right? This guy is of device Fn, right? So the order matters because when you have the n tuple of measurement results, it's paired with n tuple of timings, okay? And because we have not only what we measured, but also when we measure. This is obviously will be important. Yes, Emilia?
Exactly the same state, let's say, the same situation.
Yeah. The problem of initialization, look, this is why I call what we are doing here deduction, okay? Because if this was derivation, it would be possible to set up everything like in a linear order. That you start with some assumption, go step by step. But here, the situation is so complicated that there are like 10, 20 different threads, different plots that going in parallel. You just touched upon initialization, issue of initialization, which I will talk about it. It is obviously very vital and important that you have experiment, we want to repeat it. So there is an issue that we can initialize it in the same initial conditions, right? So we can compare the future runs of experiments with past runs of experiments. But let's ignore the issue of initialization for now, okay? Because this is another thread, very complicated thread, which will at the right time, at the right point, we will have all the tools to tackle it on and describe what's going on. So Emilia pointed out that if we want to repeat measurements, our experiments to collect data and compare it, future runs with past runs and so on, you have to have control over initialization of experiments. Let's assume that we have that control, okay? We will later down the line, we will discuss why is it possible to have this control? Because there will be answer for that. But for now, let's just assume that it is possible. So thanks for your question, Emilia. We just derailed the carefully sculpted plan. But no, it's obviously very important thing.
The problem is that they already know too much. go too much.
Yeah. I mean that's why you are role playing that you don't know.
Oh, so I'm asking you, sorry, how I should imagine this, that these times are fixed and anytime I have this collection of small f, or I have some continuation in time, so I have long sequence of time and divide this time into portions.
Yes. So in reality, I think this is what Łukasz always tells me, that when people, because what I imagine here, that the experiments, I'm saying that it terminates at some measurement. So I assume that when you do the last measurement in your sequence, you like somehow reset everything to the initial state. Let's call it state. Although when I say state, yeah, the same situation, whatever that means. We will talk about it, what it means. But Emilia is saying that, and this is how probably in practice this is most likely done, that you are, because resetting to the like real experimental setup, if you want to reset it to like the initial state, it's usually impossible to do. You just wait a bit, okay? Because, for example, you wait for some thermalization or some other process. You basically bet on ergosity to be true. So it's like you don't, there is no huge lever where you reset everything, or you just demolish your laboratory and build it from scratch, right? You just stop measuring and then usually just wait. And then you continue.
Build the system from the scratch. You have some device which produces the system.
Yeah,
If you want to have typically the systems are.
But those are like.
It's not very typical that you do plenty of measurement and you wait, you thermalize it, and then you don't know.
Mariusz, you're talking from experience of someone who's dealing with cold atoms, where you. So you have with cold atom systems, right? You don't really, it's not really possible to do sequential measurements easily, because you like, I know, release atoms from trap and let them fall on the screen, detection screen, and so this is what people thought about, initially, the destructive measurement, essentially, that it's experiment really ends with the measurements because the system was so changed that there is, it wouldn't make any sense to continue on. But there are systems like some spin qubits or whatever Łukasz is doing, that, sequential measurements are way more feasible because it's like, if you think about this cartoon of Stern-Gerlach type of experiments, right? They kinda can be realized with like solid state.
Whatever, if you wait, how do you know that the system will use the same temperature as the previous one that you made the system?
Yeah,
and
I mean,
you're doing it in a totally different system.
Now you are.
There's nothing to compare.
Now you are saying that maybe experimental physics is just, it's a bogus. It's not real. Because you are. I mean, this was this. I mean, those are when Łukasz told me that they actually don't demolish laboratory and rebuild it from scratch, they just wait for something, for example, to reset your system. I was like, but is it legal? Are they really doing what they are saying? And it's like, it's a belief that, it's okay.
They started with some thermal stuff. They wait and it will thermalize and will be the same system.
So this is basically, you are assuming typical experiment where you can do sequential measurements. People assume that ergosity is true, that thermalization is true.
The initial state was also the state which was in equilibrium with
usually.
Which is not very common.
So
but very often you prefer some
for our purposes, if
you assume that the initial state was in the equilibrium thermostat, that's okay. You do something, you have the same thermostat somewhere, you wait, and you will have the same system.
I mean, it's kind of okay. I think people know what they are doing. The experiments are reliable. But for our purposes, let's assume that, you know, when the student ends their run of experiments, we blow up everything, grab another student, build for them new basement.
We don't have to keep this.
Well, just to make sure that, you know, everything's reset. We just have to make sure that everything's reset, you know. Well, I already been through that, you know. But, you know, just to make sure everything was reset, we blow up everything, you know, salt the earth and make sure. So we are naively thinking here that it really can be, because we don't want to put in too many assumptions here. We just the assumption is that we have infinite money and resources. We can, you know, reset everything.
Better to assume that instead of blowing the student with laboratories, to assume that we are able somehow to produce ideal copies.
Yeah, okay. You know, that's a. This is innuendo for.
We have some devices which we students like car factory. You know, they are identical.
Yeah, okay.
They go out to measure.
If you fancy more humanitarian approach, okay, you don't like explosions, then yeah, you have a factory of students. Okay, you get them from the production line. You know?
How do you make sure that this next students will not communicate with the previous one? Because this is what actually students usually do when they make the measurements. They say, "Oh, I get this kind of result."
You know, that's why blowing up is that's why blowing up is so good. You know, just make sure.
I understand your point.
Okay, so anyway, so initialization is very interesting, and there we will get to that, and it's very interesting.
We have collection of samples of F, which are obtained under the same condition, like temperature or.
Not at the same, at the pre-selected moments of time, 1, 2, and 3, and you just repeat the experiment by pressing a button on a device at time t1, and then you press the button on device f2 at time t2.
Yes.
You pre-select this time, and not at each moment. You read time.
Yes.
I like to say that you deploy the device. Okay, this is.
It's obtained under the same physical conditions. Let's say. Like
The experiment. Yeah. You know, the experiment is reset conditions and this.
That's not the devices that clicking randomly and you don't control it.
Yeah. Oh, yeah. Okay. This is important. Although Mariusz is touching upon important distinction here, because you could imagine, and this is there's a whole branch of quantum measurement physics about it, that you are like monitoring the system. So it's like you are just this.
Quantum system.
Yes. So basically you are just waiting for clicks of some detectors. Okay. This is not what we are talking about here. Okay. We are not waiting. The time when the measurement happens is not a stochastic variable. Okay. You are deliberately deploying the device, and when you do, it does a measurement. Okay. It displays something for you, and presumably it does something to, you know, it's not just random display.
Nothing.
No.
Because typically when I am measuring photos, I have camera, and there are some moments when they arrive and some moments
measuring.
I can open my
standard setup. No empty.
This is my question.
No empty. Because
zero is also an example of measurement.
Yeah, but this
No, it means
not measuring something. This is this monitoring setup, you know, because
that your device is such good that anytime you employ it, it will produce the result.
No, I'm assuming that you don't wait for it to do measurement. When you do measurement by deploying the device. Okay, because this you know, empty clicks of the photo multiplier or whatever, when you do optical experiments, this is a monitoring setup in my view. Okay, because you're waiting for photons to come in, okay?
When I have camera, I can, I have a shutter that I can employ it when I want, okay?
Yeah,
So-
yeah, this is what we are talking about.
and I can take you pictures of you at times that I assumed probably
Yeah.
that you will be still there. However, if it will be very long, let us assume that we are measuring photons by this camera. If the number of photons is extremely low, even if I open the shutter.
I don't think there is a much value in talking about the quality of detectors at this point, at least. Low quality detector,
We assume that
low quality device is just device that has its collection of the meaning of the.
that is always a photon that you measure. You can measure this single photon many times.
It's
and it will never
taking
escape.
the picture, okay? So maybe the dark.
Taking a picture in the dark.
Yes, so maybe with a photon detector, you're taking the picture. So you are opening your photon multiplier, and 0 photons, 1 photon, 3 photons, 4 photons is one of the results in this set omega f. Maybe this is the solution. But the distinction I want to make is
number of photons. If the observables that you measure is number of photons, then it is okay. Number can be 0.
yes. So I guess that this is, but the
observable will be okay.
the distinction I want to make is that there is a point in time we choose when to deploy the device. You're not waiting for it to click for it. Okay, so it's not the time of the deployment of device is not a random variable. Okay, or you control it. So monitoring versus let's say canonical measure. I don't know how to, because this is the standard quantum mechanics really gives you prescriptions how to describe those deliberate measurements, not monitoring. Monitoring is a subfield of quantum mechanics, which I'm personally very critical of. I don't think it's a well-formed theory, but people are doing it, and we want to steer away from that. The dream is to, once we are done with this, to then describe the monitoring setup with what we will have here, okay? But this is the distinction that has to be made, okay? Deployment at times. So you see, this is very interesting approach, because all those things. This is the great opportunity to talk about those basic things, which usually we are just taking for granted. And here is we can talk about some assumptions and setups.
Monitoring is make this measurement at well prescribed of measurement is monitoring at well prescribed moment of time. There is no, I think, any fundamental difference except of this time.
Well, I think there is some kind of.
If I monitor the system at well-defined moments of time only, that is a measurement. So I don't see any fundamental difference between monitoring and
well, okay, so
measurement. When you monitor only, even if you monitor it continuously, you can take this well-prescribed moments of time. If you have some sequence which is measured in your language.
So that would be sequential measurement, right? Yeah. But I think that there is difference between, because this doesn't describe when the time of measurement is when you wait for the detector to click. That's something different, because then when the measurement happens, the time is another variable here, right? Then becomes so. It has to be described differently than what we are doing here. That's my. So my this is a kind of tangent. Maybe it's boring for people, but for me okay, let's not go to this tangent. Mariusz is his experience with monitoring, and so
to think the way you think, so I maybe you should.
yeah. So if you are
this point of view, but
even if you are doing very dense,
difference to me, and maybe there are some details which might.
So if you are thinking about,
want to discuss it now.
if you are thinking of monitoring in the sense that you are just doing measurements very frequently, then that would still be sequential measurement, just very dense. There is a phenomenon associated with such frequent measurements, which is one of our phenomenological observations. When we get there, that would be a good moment to talk about measuring versus monitoring versus frequent deployment of devices. But so let's end this tangent for a bit, so we don't forget where we were. Oh my God, there is something wrong with the camera. Okay, so let's reel it in, and we'll make a break soon. Okay, just to this time, let's not do the marathon. We have time. I believe we have time. Okay, so our experimenter does their experiment where they have some conditions which they can reset back to, and they start deploying the devices at times of their choosing, device of their choosing, at time of their choosing, and they are reading the n tuple of results that is associated with n tuple of times. Okay, and now we want them to repeat all those experiments with different number of different timings, different number of measurements, different collection of devices. We want them to collect all the data that's possible. Okay, so they just spend their whole life in there, like this guy Tycho Brahe, right, Mariusz, locked in the tower and just recorded astronomical observations so that Kepler could take them and Kepler laws. Not wasn't? Okay. But the idea is that if you do those, you repeat experiment many times with a given setup, that is given just 1 minute and we'll take a break. Okay. So now you collect all this data for each experiment, for each setup. So for each choice of the sequence of devices and timings, you repeat it infinitely many times. And once you do, you have all this data, you can estimate from this data a probability distribution that governs this particular setup. And you will get, this will be a multivariate probability distribution that's indexed by timings. Okay, so from this infinite number of repetitions, you have a lot of students. Infinity is not so impossible. So this gives us estimation of, and we'll have probability distribution. So we'll have P in subscript. I will use subscript to store timings. Okay, superscript to store the devices, and argument to the results. So this is probability distribution. Prob dist. And we'll be using a shorthand notation because, writing all those sequences is very tiresome, very fast. So we'll be using this tuple notation. Okay, so n tuple of choices of devices, n tuple of choices of timings, n tuple of results. Okay, so in the text there is a boldface font, okay, for tuples, but boldface font I cannot do them here. So arrow. There will be some conflict of notation at some point, but we'll manage it. So now, if they now do the experiment for many all the choices of n, all the choices of timings, all the choices of devices, we have a lot of students, infinite time, infinite resources. You can do it, and you can for each experiment you estimate those probability distributions, and you do infinite number of experiments, so you have whole family of those probability distributions, okay? And you could do it for classical systems as well, with classical devices, and the same kind of description would apply, in terms of probability distributions. So once you do all those experiments, you do the estimations, and we believe that they are, the best estimations possible, very accurate. The students really, use the correct techniques. This collection, this family, infinite family of probability distributions, gives us complete quantitative description of the phenomenology of our system. Okay. So when I talk now about examining, analyzing phenomenology or experiments, I'm specifically talking about analyzing those probability distributions. Okay. All right. So this is our figure of merit. Our deduction will be based on figuring out some properties of those probability distributions. Okay. Depending on the choices of times, number of measurements, and finally the devices. The devices will be like, as you can imagine, this would be the most important part of this whole story. But also 100 years ago, they were one tuples. They were using one tuples. So only one time, one device, one result. Now we are doing it for n. Okay, and this will be the structure of those probabilities will prove to be very, very much richer than just. It is a big step, and it's really big step in this case. Okay, essentially, if you just did one tuples only, you wouldn't be able. So you would try to do in this way. So you just take the P, T, F. So only for single measurement, and you will try to deduce some formalism of any theory from that. You would fail, okay, because it's too simple. It's just standard probability distribution that doesn't have any very special properties. You have to do more. I mean, the only thing you could do, if this is the only thing, you don't bring anything else, any other information from any intuition, any. Yeah. I mean, it would be just the only thing you could do is to tabularize those probabilities, essentially. That because there is not enough structure in just single measurement probabilities. But you go to many, and all of a sudden there is explosion of weird behaviors. Okay. So let's take a break. Okay, so let's continue. All right, so we have our probabilities, right? So there are, I don't know, we took us a lot of time to get to this point, which is like in my notes is the first paragraph, okay? Now I'm thinking, do I want to go straight to phenomenology, talk about experiments already, or spend a little bit more time on the probabilities? But maybe let's spend a little bit of time on probabilities, like very short, very small, targeted review of some of the theory of probability theory, because you know, there are listeners on different levels, okay, let's say, and there are some, people think they know what probabilities are. They just, oh, we're using all the time in physics, but surprisingly, there are a lot of important things about probabilities that not many people know about, okay? Some nomenclature about it, which is very useful, and we will using some advanced measure theory at some point. So maybe it's a good idea to start when everything is very simple, to just introduce some very, very simple ideas, but expressed in more advanced language. And there will be also some physics in this story. So let's talk a bit about maths. Mathematics, intermission. Theory of probability. Probability, or if you want to be very fancy, some measure theory, as it is called sometimes. So some glossary. So we are dealing with probabilities, and there is people have some language, right, for describing certain things in this probabilistic description. So for example, our n tuples. So we have our n tuple of result, right, which is a sequence again. So this thing is an element of this kind of Cartesian product of those result spaces of each device. N minus 1. Okay, like with vectors. 1, and this will come up a couple of times. So again, shorthand notation. So this Cartesian product will use pseudo vector notation as well. Okay, when you see this is what it means. So in theory of probability, so this is a result of our sequential experiment. So this is called sample space. So this is sample space for our experiment. Okay, and this is all possible results that we can observe. Okay, hence this is how they call it. But aside samples, there are also events. Okay, so getting one such tuple as a result is a singleton event. So there is just one concrete thing happened, right? So so this probability that we wrote down. So formally, this is the same as a probability measure shall we use the same symbol to denote it, of a singleton event. So a set composed of this one sequence. Okay. So this is singleton event. That's pretty boring, not very interesting.
You get the difference between the left and right hand waiting.
There is
This is what equality does.
there is a formal difference here. I'm abusing notation a bit, okay, but this is a good abuse. There should be a different letter. Yeah, so this is probability prob measure, and this is probability distribution. Formally, this guy here is a function from this is the function from sample space to something between 0 and 1, right? Because it's probability. And this guy here, formally, is a function on sets, which represent events. Okay, so how they write it in the probability theory, this will be useful. Okay, so they write it that it is a function from they call it power set. This will be, I promise, this is not a complete waste of time. From power set to 0 to 1, and the power set is a set of all subsets. I will explain myself immediately. So this guy, so this is the set that contains the empty set. It contains whole set, whole sample space, okay? It contains all the singletons, all singletons, and all unions of singletons. All set unions of singletons.
So this notion of the thing on the right is broader. It's such a probability measure. Or
I will explain. I'm explaining immediately. So this is power set. Power set. You can check it out on Wikipedia if you want more formal. Because in like the real hardcore advanced theory of probability is it's also a theory of integration. It's also a theory of measuring volumes and stuff like that. Okay, so it's about assigning number to a collection of items. Okay, so in case of calculating volume, that's pretty obvious. If you're calculating integrals, that's also kind of obvious what's going on. But if you're representing probabilities, so the singleton, like this guy here, the singleton represents that event where we observed the specific sequence of results, right? But you could have you could take a union of two singletons. Yeah, for example, yeah. So you take
this sequence,
this sequence or measuring
class,
one by one.
Yeah, this sequence, and that's the joint probability of having.
So you had this kind of event, okay, which also equals union of singletons.
But the set seems to be separate. Isn't it so that joint probability of having two particular sequences is the sum of this probabilities to the right?
Yes, this is like this is the property of all probability measures, because this event, when you have a union of one singleton, the other singleton, is an alternative. Okay, I observed F, or I observed F prime. Okay, so this is how you construct, how you represent events where you have some, manipulate constraints of what you observed, right?
So this is equal that for the empty set you would assign zero, for the whole thing you would assign exactly one.
Yeah. So if you want to have a proper probability measure, okay, according to the theory of probability, this probability measure would, like you said, the properties it would have to have. Zero on empty set is always zero, has to be zero. For whole set, should be one. It's normalization condition, okay? And it has to be additive, which means that whenever you take of any union singletons, so you take some union of couple of singles, some alternative, okay? It is a sum. This is called additivity. It's the same as taking a sum all right, which is the same in this case as summing over. So we are abusing our notation full blown, right? So in case of this is simple like that because we have a finite, our sample space is finite, okay, it's finite dimension. This all business stops being so simplistic when your sample space is, for example, real line. Then this is what the theory, this is the purpose the whole theory was built for. But we are avoiding that. For us, everything is simple. This is an observation that what I tried to say here is that because any event, so any element of this power set, is some kind of union of singletons, okay, and because probability measures are additive, right? So any alternative event representing alternative is sum of the probability distributions, okay? We only need to know to specify those probabilities for singletons to describe every possible event that could ever happen, okay? So that's why we forced our students to estimate those probability distributions, because once we have them, we can describe probability of any event possible, okay? Any kind of question can be answered using some combination of those probability distributions. And this works because we are using finite sets. If non-fine, real lines were engaged, you have to do much more, okay? So let me illustrate it with, okay, no. One more point, which is very vital to underline this. Oh, that's ugly. I can do better. can do this like this. Straight line. So we are our students, our slaves, essentially. They collected the family of probabilities, those probability distributions, right? We have whole family, infinite. And they are. This is crucial that they they are indexed by those timings, right? Because whenever you do your experiment, when you do your measurements, even if you use the same devices, right? The same number of deployments of devices, but what you will observe will most likely, in general, depend on this the choice of timings, right? So even though, so in other words, if I have a result that's represented by this n tuple, right? That's a element of this singleton, element of something like this. And I obtained it, obtained at timings Tn, okay. But I could also get the same result, same tuple, versus obtained at different times, different timings. Also n times deployed, but at different, a little bit different timings, right? So even though this is the same sequence of results measured, right? But the experiment in first case would be described using probability, this probability, right? Or this measure with this set of indices, which is again power. If it's measured, so it's a power set to 0, 1 versus Pn prime, which is also a function from the same event space. Formal. This is the same kind of results you can obtain in the experiment done at timings Tn. The same kind of results you can observe for times of timings Tn prime, but the probabilities will differ, right? The sample spaces are the same, but the times are different.
This set does not have any index which would indicate the time.
Yes, that's what I am saying.
You should add some index to this.
No. You see,
you should somehow.
No. This is what I'm saying. The results you observe are, the possible results are the same. The difference lies in probabilities. So you have function, this function, you have this function here, and the timings are encoded in those functions, not in the domain of those functions. So, I mean, you could make it like promoted from this subscript to like another set of arguments or something like that. But this underlying logic.
Like for single signal, one measure.
Mm-hmm.
This will produce a number from 0 to 1.
Yes.
Then you take the same argument because there is nothing which tells you about the time. You will get the same value. However, probability of the two events are different.
Yes, because probabilities depend on timings. This is what I want to say.
What this measure tells
about?
I
How
mean,
much volume the
well, it's a, you can, you know,
Was it useful for anything then? Is it useful for to have this,
I want,
to know this probability, this powers,
to
know this measures? Is it useful to know this measures?
I mean, like I said, those measures are the same as probability distributions, right? Ultimately, I want to say that the timings are a part of, you know, so for one set of timings, you have probability distribution. If you change timings even a little bit, you have different probability distributions. And they formally describe different events also. Even though the measuring results could be the same set of possibilities, but the timings are crucial. Those are different events immediately if you do something with timings, okay? And so there is no like purely logical or mathematical reason why the probability for certain set of timings would be in any way related to probability with slightly different timings. If any such relation exists, this is purely for physical reasons. You have to identify it through observations, through experiments, okay? And let me illustrate it with an example, because there is these are our probabilities, and we believe, they describe everything that about the experiment. And because we are classical beings, there is certain amount of intuitions we involuntarily project on those probabilities. And now, bearing in mind, this thing I said, that there is no purely logical connection. The logic doesn't require any connection between probability distributions with different timings, okay? Only physics can enforce that. Bearing this in mind, let's consider the following example, which I don't know if it will be, for you will be intuitive, but this is some example. So, according to, because the probability measures are additive, so you can consider we take our probability, and let's single out here jth argument, okay? For a moment, tj. Sorry, T1, F1, Fj, F1, and let's do operation that's called marginalization formally, so, which means that you take this probability and you average it over the jth argument, okay? And this is called marginalization. This sum. It's called marginalization. So by marginalization, you essentially eliminate one of the arguments. So you take your n probability distribution for n variables, and you get rid of one of them, the jth, the one corresponding to timing tj. It's called marginalization. This sum, this thing here is this marginal, as it's called, is a proper probability distribution still, okay? Just on smaller sample spaces, okay? Smaller event spaces. But now, due to additivity of probability measures, this sum, we can convert it into a union of sets, okay? Like we could convert union into sums, so we can do it backwards. So due to additivity, we can write it as a so a union over Fj belonging to Fj here. We have our singletons here, which you can write it as a more formally, let's say, as a set made out of sequences such that Fj is any one of the possible results displayed by a device deployed at time tj. So this guy here, this is a mathematical, we just calculated something, but this event here is, we can interpret it, what it means. So what this event means that, okay, we are doing measurements and we are considering an event where all the results are set to certain values. So Fn is certain Fn, Fn minus 1 is certain Fn minus 1, and so on, except of Fj. Fj can be whatever. There is no constraint on Fj. Okay, it's whatever the device could display. So intuitively, I don't know how your intuition works, but this is very common intuition for usually common intuition, that if there is no constraint of Fj, it can be whatever. So this event should be equivalent to event where the device at time tj was never deployed. Because no, it's whatever value displayed goes through. So it's like, essentially, I'm not asking anything about this moment in time. So intuitively, this should be equivalent to saying that, okay, so it's like I never did the measurement at this time j. So if this intuition is correct, that would mean that this marginalized probability would be equal to probability where we never did measurement at time tj. Do you feel this is intuitively correct? If not, don't worry, I will explain why it is intuitive, even if it's not intuitive for you, but later down the line.
If you repeat it many times, the intuition will tell you.
Yeah, the intuition will form.
You will form the intuition. It's like you have intuition with particle balance to the values. It's intuitive.
Yes, so here. So here, by by using intuitive notions, I connected here a probability associated with n timings with probability associated with n minus 1 timings, essentially. So there is no purely logical mathematical reason why it would be so. This connection is, I'm basically, I'm postulating something about physics here, okay? My intuitive understanding of physics is that this should be the case. So to really check if this is the case, you have to confirm it with observation, with measurements. And this will be our, okay, so what I did here is called foreshadowing, okay? Foreshadowing, because this will be our essentially first phenomenological observation. And I will explain the intuition where it's classical. The postulate thing I postulated here is intuitive for classical observers, but quantum mechanics will have a surprise for us, okay, at this point. And we could go to discuss those observations, or here's a poll. Do you feel tired enough to stop here and continue on next week? Or talk for 20 more minutes about Mariusz Emilia? You're in mixed state. No, you know what?
And then you have seminars on
Yeah.
No,
No, you know what? No, it's a good place to stop because okay, because because there will be big. We will talk about like two simple observations, and there will be a huge tangent which will be like fundamental for all this to understand what's going on. But the idea, you know, this events and connecting the probabilities through physics into what is intuitively expected, this is like to bear it in mind. Okay, so let me. Okay, so this is the moment where we can stop and.